Okay, so today we're going to talk about higher derivatives. And so let's kind of get into what we mean by higher derivatives. So far, here's what we know. We know that f prime is the derivative of f, okay? And so what we could add on to this is we could say, look, in fact, f prime may have a derivative of its own, which, if you think about it, if I were to say f prime having a derivative of its own, how would I write this? Well, it would be denoted as f double prime, right? Which, what does this make sense, right? Because f prime is the derivative of f double prime is the second derivative of f, or simply just the derivative of f prime. So I'm basically finding the derivative of this guy, which gives me f double prime, which this is also called the second derivative. And it's also written as d2y dx squared. So notice how this is saying you're finding the second derivative. So anytime you see this d squared y dx squared, just understand that we're saying that this is the second derivative of y with respect to x. So you might be wondering, well, and by the way, this is in Leibniz notation, which remember dy dx means you're finding the first derivative in Leibniz notation. So you might be wondering, wait a minute, how is this actually the second derivative? So think of it this way. Every time you find a derivative, see, think of it this way. Let's make a comment here. Note. Think of it this way. Dx of y means what? Find the derivative of y with respect to x. So think of it this way. If I'm finding two derivatives of y, or if I'm finding the second derivative of y, what does that mean? We need to, so this is actually the first derivative of y. So how would I find the second derivative of y? I would have to take d dx twice. So in other words, d dx times d dx of y means what? I'm finding the first derivative of y, and here's the second derivative, which if you notice, this actually breaks down to d squared y dx squared. So there's two dx's and two d's, and that's how you get this notation, okay? So I'm sure you could pretty much guess, well, what does the third derivative look like, and so on, okay? So just to kind of comment on that, what we notice is f triple prime, I'm sure you could guess what that means. This is strictly the third derivative, okay, which means you're finding the derivative of the function f 3 times, okay? And so after the third derivative, we no longer put these hashes anymore, because it's kind of like every time you put this, I mean, what am I going to do for the 15th derivative? Am I really going to put 15 of these lines and go on forever? So what happens is after the third derivative, we commonly just write a number above it. So f4 would mean this is the fourth derivative. And of course, if you see fn, that's the nth derivative. Okay, so basically what we're saying is we could find multiple derivatives over and over and over. Okay, so let's just look at a quick example, and then we'll finish up this section talking about the position function, because if you've noticed, we've spent quite a bit of time on the position function. So for example 1, we'll say find the third derivative of f of x equals to e to the x plus sine x. Okay, so here's what we know. If that's f of x, so to get to the third derivative, I first need to find the first derivative. So f prime of x will be, now let's just find the derivative. So we're using the rules that we've always learned. So the derivative of e to the x is just e to the x, plus the derivative of sine x is cosine of x. Okay, and then f double prime of x, what would that be? Well, that means find the derivative of f prime, which would give me f double prime. So then the derivative of e to the x is still e to the x, and then the derivative of cosine x is negative sine x, so it'll be minus sine x. And finally, f triple prime of x would be, and we find the derivative of the second derivative to get that, which means the derivative of e to the x is e to the x, and then the derivative of sine x is just cosine x, so it'll just be minus cosine x. Okay, and there you have it. We found the third derivative of e to the x plus sine x, which is e to the x minus cosine x. Okay, so this section is actually extremely short because I feel like most of it we've done prior to this. All we're doing is we're just finding further and further derivatives. Okay, so there's nothing for us to worry about. But let's turn our attention to the position function, because we know something nice happens when we find the derivative of the position function. And in fact, I'm sure you could answer that question. Okay, so what we have learned is, we learned last chapter that given the position function, we have the following. In fact, the first derivative is what we mainly talked about. The first derivative represents, and you should already know that, the first derivative, or the derivative of the position function, which is literally what the first derivative is, that represents the velocity. Okay, so this isn't anything new to us. Now, my question is, what's the second derivative of position function? And how do you find the second derivative of position function? Don't you just find the derivative of velocity? Now remember, derivative means what? Instantaneous rate of change. So if I find the derivative of velocity, which is pretty much the second derivative of the position function, what is the instantaneous rate of change of velocity? So if you think about it, what causes velocity to change? And if you're driving a car, let's say, and you speed up, what are you doing? What's causing you to speed up? You're accelerating. Or if you slow down, you're decelerating. So in fact, what you notice is that the derivative of velocity, which is the second derivative of position, is called the acceleration, okay? Which, notice how we're actually making sense of what's going on here. So the second derivative of the position function, that represents the acceleration. Okay, and so when we say acceleration, in other words, another way to think about it is, this is the second derivative of position, or another way to think about it is just the derivative of velocity. So this is the derivative of velocity. Okay, so the last thing we're going to talk about is the third derivative. Okay, and so the third derivative is kind of harder to think about. Okay, so what we could say is that the third derivative of the position function represents the jerk. Now, when I say jerk, we're not saying, hey, you're a jerk. Let me kind of make sense of what we mean by the jerk. Because if you think of the derivative of the third derivative of position, or in other words, what is this? It's the derivative of acceleration, right? What causes a sudden change of acceleration? And the sudden change of acceleration is what we call the jerk. And think of it this way: the one example I could give you that would probably make sense is if you've ever sat in a car where the transmission isn't doing too well. What do you notice when the car changes gears? What happens to the car if it doesn't change gears smoothly? You kind of have that jolt. It's like a sudden jolt or a sudden jerk that you get, and that's what you have. So when a car's transmission is about to give out, it shifts gears in such a way where you kind of get this jerk feeling, or you kind of move forward, or you could feel your head moving back and forward because of that sudden jerk or that sudden jolt. And that's what happens. And if you think about it, these car manufacturing companies, when they design these transmissions, what do? They come up with a function that describes the position of the car and so on, and then they find the third derivative. And their goal is, if the transmission is going to be smooth, they want to set the jerk equal to 0, because if the car's transmission is very, very smooth, and you don't want the person to feel when your car is changing gears, what you want to do is you want to set the jerk equal to 0, so the person driving the car doesn't feel the car changing gears. Okay, so that's basically what this is. So the jerk is literally just a sudden change in acceleration. Okay, another thing that I could point out is, for example, if you've ever been at Magic Mountain, which I think most of you probably have, if you've ever sat on Superman, what happens, like when the ride goes and all of a sudden you stop, what do you feel? You kind of feel that pull, or where you're kind of like you're being pulled forward and backwards real fast. It's because it's that sudden change in acceleration which causes your head to move forward or to jerk. Okay, so that's kind of what this is all about. So just to quickly summarize this, if I give you the position function, the first derivative of position gives you velocity, which that's nothing new to us. The second derivative of position, which another way to think about it is the first derivative of velocity, gives us the acceleration of the object. And then the third derivative of position, which is, in other words, the first derivative of acceleration, that's known as the jerk function. Okay, so that basically wraps up this section. Remember, the whole purpose of this section is to find higher derivatives, which means we can go past the first derivative. We could find a second derivative or the 10th derivative and so on. Okay, so as far as following your rules of derivatives that you've learned in the earlier sections, we're still going to use those. Okay, so you might need to use the product rule or the chain rule or the quotient rule and so on, except now we're just finding multiple derivatives. So that basically takes care of this section.